Successful people think differently because they're not worried about other people's judgment. While the world criticizes, they create. While most people are busy protecting their reputation, they're too busy searching for the truth. And here's the key. Thinking differently is not an aesthetic choice. It's an intellectual survival skill. If you think like everyone else, you'll end up with the same results as everyone else. And the average is harsh. Uninspiring jobs, lives with no purpose, routines where people wake up, work, complain, and go to sleep. Nothing more. Is that really living? Or is it just surviving? Pay close attention now, because this may change the course of your life. Think differently or die average. Stop believing what everyone else believes. Stop repeating what everyone else says. Every success story begins with someone who dared to disagree with normality. Not because they wanted to look rebellious, but because curiosity was stronger than the fear of judgment. And it's this curiosity, directed and disciplined, that opens doors the average will never see. So think differently. And if you decide to think differently, prepare yourself for something greater. The freedom to learn anything, to create paths no one has created, to master your own mind. Listen carefully now, because what I'm about to reveal lies behind every genius mind: curiosity. Ordinary people lose curiosity over time. They accept ready-made answers, stop asking questions, stop investigating. They think they already know enough. And that's the moment mediocrity sets in. Now look at the people who truly stood out. Scientists, entrepreneurs, creative leaders. They all had one thing in common. They never stopped asking questions. Even if they didn't understand something, they would ask again and again and again until the answer finally made sense in their mind. This is the first step to thinking differently. Many people are embarrassed to raise their hand and say, "I don't understand," afraid of being criticized. In a classroom, the student who asks too many questions is easily labeled as stupid. But the truth is exactly the opposite. The one who asks questions is one step ahead. The one who questions shows the courage to learn. That's why, if you want to start thinking differently, begin with the simple act of admitting your doubt. The courage to ask is the mark of someone who refuses to remain ordinary. Now pay attention to me, because I'll show you how to truly think differently. Thinking differently is a daily exercise in intellectual freedom. The first step is to do what you love. When you work or study something that sparks passion, your energy multiplies. Normal is waking up tired because you spend energy on activities that don't inspire you. Different is waking up hungry for life because you're investing your time in what makes sense. Ask yourself, if nobody judged me, what would I choose to learn, to create, or to build? That answer points to your true path. Second, protect your mental independence. That means not letting other people's opinions become the filter for what you think or do. Most people fear being criticized, fear being called strange. But remember, everyone who changed the world was ridiculed before they were applauded. Thinking differently always bothers people because it exposes the mediocrity of those who follow the herd. Third, feed your curiosity without fear. Ask, test, explore. That's the fuel of innovation. Don't accept anything just because everyone does it this way. Ask yourself, is there another way? The simple act of questioning already puts you on another level. Fourth, simplify your life to free up energy for the essential. Those who think like everyone else get lost in excess. Those who think differently focus on what matters. If you're exhausted, it's hard to have the clarity to think in a new way. Energy is born from being aligned with purpose, eliminating the unnecessary, and putting strength into what truly moves your life. Pay close attention now, because what I'm about to tell you is one of the mind's biggest prisons, the fear of being different. Most people don't live their own ideas. They live other people's ideas. They're shaped by the opinions of family, friends, society, the media. They spend life trying to please, to fit in, to be accepted. But those who think differently understand something simple. If you always seek approval, you'll never have clarity. To think differently, you must learn to shield your mind against the pressure of the majority. And that starts with a daily exercise. Every time you feel tempted to do something just because everyone does it, stop and ask, does this really make sense to me? Does it bring me closer to what I want? Or does it just make me like everyone else? That simple question is enough to expose the automatic choices that keep you stuck in the average. Remember, life is too short to live dependent on other people's approval. Another point, choose carefully the voices you listen to. I'm not saying ignore everything and everyone, but be discerning. Ask yourself, does this person have results I admire? Do they live what they preach? Or do they just repeat what they've heard? If not, why give their opinion so much weight? Learn to separate constructive criticism from noise. And here's a powerful detail. The courage to stand by your own vision earns respect, even from those who disagree. At first, you may be criticized. You may even be ridiculed. But over time, when results appear, the same people who laughed at you go quiet. Nothing is more convincing than the evidence of a life lived with purpose and authenticity. Thinking differently is swimming against the current. It's bearing the pressure of judgment without giving in. It's choosing the clarity of your conscience over the empty applause of the crowd. And when you train yourself in this, you realize that freedom isn't being accepted. It's living true to what you believe, even if no one claps. Thinking differently isn't an inborn talent. It's a trained habit. You're not born outside the box. You build the box and then learn to break it every day. That takes discipline, and discipline is born from rituals. If you want to stand out, you need to turn curiosity and mental independence into concrete actions that shape how you think. The first ritual is the daily question. Pick any situation in your life and ask, why is this done this way? Don't accept the first answer. Go deeper. Who said it has to be like this? Is there a better, simpler, faster way to do it? When repeated every day, this exercise trains your mind not to settle for ready-made answers. The second ritual is explaining out loud. When you learn something new, don't keep it to yourself. Explain it. Even if it's to the mirror. When you speak, your mind organizes, your ideas align, and the gaps show up. That's the moment you discover if you truly understood. This simple habit will accelerate your ability to learn 10 times more than someone who only reads and repeats. The third ritual is creative review. At the end of the day, take one idea or important concept you learned and recreate it in your own words. Use a metaphor, a story, an example from your life. This act of recreation makes the idea stop being external and become part of you. It's in this act that different thinking begins to flourish. And finally, the ritual of conscious observation. Set aside a few minutes to observe something ordinary and ask yourself, what is no one else seeing here? It could be an object, a situation, even a conversation. This practice trains your eyes to see beyond the obvious. That's how innovations are born, from someone who looked at the ordinary and saw the extraordinary. Those who practice these rituals don't just think differently, they begin to live on another level of perception. And that difference builds up day after day until it becomes an advantage impossible to ignore. But here's the truth. The path of those who think differently is never easy. They are misunderstood, judged, often humiliated. The crowd cannot stand those who break the pattern, because independent thinking exposes the mediocrity of those who prefer to follow the herd. It's easier to call someone crazy than to admit they might have seen something you didn't. But listen, every great person you admire went through this. Galileo was condemned for seeing beyond what the church accepted. Bruce Lee was ridiculed for mixing styles and creating his own philosophy. All of them were seen as too different until the world had to bow to the evidence of what they built. And here's the secret few have the courage to accept. Thinking differently is expensive in the beginning, but it pays dividends forever. The rejection you feel today is the same energy that will fuel your victory tomorrow. This is the path of those who refuse to die average. They choose truth over acceptance, curiosity over indifference, courage over fear. And with that, they build something that lasts, something that inspires, something that cannot be erased. So I tell you, if you want to think differently, be prepared to be misunderstood, be ready to be criticized, but also be certain that in the end you will be remembered. Because no one remembers the crowd that merely repeated. History remembers the names of those who dared to be unique. Think differently, protect your flame, and never bow to mediocrity. Because in the end, you either have the courage to live as an exception, or you accept dying as just another in the average. Now it's on you. I want you to prove to yourself that you've chosen to think differently. Write in the comments, I will never accept dying being influenced. This phrase is more than words. It's a pact with your mind, a declaration that you will not bow to mediocrity. And if you enjoyed this lesson, leave your like. And don't forget to subscribe to the channel and hit the notification bell, because here you'll keep receiving ideas that will challenge your mind, expand your vision, and accelerate your learning. Remember, those who think like the majority live like the majority, but those who choose to think differently.
The word law sounds confident, final, as if reality signed a contract and agreed to follow it forever. In physics, the word is used with that same seriousness, but without any assumption of authority behind it. No one enforces a physical law. Nothing checks compliance. There are no penalties handed down for violation. The law holds anyway. That alone deserves attention. There is no built-in requirement that the universe behave consistently. Nothing demands that the same setup, repeated at different times or places, must lead to the same outcome, and yet it does, with reliability strong enough that entire technologies, predictions, and measurements depend on it without hesitation. A physical law is not a command given to nature. It is a regularity discovered through repeated failure to find exceptions. Drop an object, heat a metal, charge a capacitor, send light through glass, change the location, the time, the observer, the surrounding conditions. The relationship repeats, not approximately, not most of the time. The same connection appears again and again. That repetition is the strange part. Physical laws do not explain why the universe behaves this way. They describe how reliably it behaves this way. Take gravity. Objects accelerate downward at a predictable rate near Earth. The law does not instruct the object to fall. It states that whenever mass and distance appear in that arrangement, the same outcome follows. The law is a compressed summary of behavior written after observation. Physics does not invent laws and impose them on reality. Physics notices that reality refuses to vary in certain ways. A law is what remains when preference, intention, and opinion are removed, leaving only what repeats no matter who checks. This leads to a consequence people often overlook. If something violates a physical law, it does not qualify as rare or unusual. It simply never appears in experiments, regardless of how carefully the conditions are arranged. That is why physical laws feel absolute. They are not supported by authority. They are supported by every failed attempt to break them. At the same time, these laws are restrained. They do not specify everything that will happen. They limit what cannot happen, regardless of clever design or effort. That restraint is exactly where their strength comes from. Taken seriously, laws stop resembling rigid formulas and start resembling the framework holding everything else in place. And that leaves a question that refuses to disappear. If the universe follows laws so reliably, where do they come from? And why does nature obey descriptions written by creatures inside it? That tension sits at the center of physics, and it does not resolve easily. That question stays in the air because the word law quietly pushes the mind in the wrong direction. A physical law often sounds like a powerful rule running the universe from behind the scenes, something active, something in charge. But at the deepest level, a law is none of those things. A law is a relationship. More exactly, it is a relationship that stays the same while everything around it changes. That is what separates a law from a coincidence. Materials can change, locations can change, sizes can change, conditions can change, and yet the same connection between quantities keeps showing up. The law does not live inside the object being studied. It lives in how measurements stay linked across many situations. This already pushes against how people usually think about rules. Rules often sound like instructions. Do this, avoid that. Physics does not operate that way. Objects do not check a rule book before behaving. Nothing pauses to see whether it is allowed to move. The law is never consulted. The law is written afterward. What physicists actually track are numbers, distances, times, masses, charges, speeds. One value is changed, another responds, and the search is for a link that refuses to disappear. When that link survives every attempt to disturb it, it earns the title law. So a law is not something the universe follows. A law is something the universe never contradicts. That difference changes how the whole subject works, because it means laws do not push events forward. They sit above events, describing how behavior stays tied together across many cases. This is where everyday thinking tends to slip. It feels natural to say a law causes behavior. Gravity causes falling. Electrical laws cause current. But the direction is reversed. Objects behave first. Laws are written later to describe how that behavior stays connected across different setups. The law describes consistency, not control. A simple example helps. Take a spring. Pull it a little, it resists a little. Pull it more, it resists more. Double the stretch, double the resistance. Change the spring, and the exact numbers change, but the link between stretch and force stays. The law is not hiding inside the spring deciding how to respond. The law captures how two measurements stay linked over many trials. At its base, that is all a law ever is, a stable connection between quantities. Now comes a part that often surprises people. Laws do not describe events. They describe limits. A law draws boundaries around which relationships are allowed to exist. Inside those boundaries, many outcomes remain possible. Outside them, nothing ever appears, no matter how carefully the setup is arranged. That explains why laws feel strict without being detailed. They do not tell you what will happen next. They tell you what will never happen at all. This role becomes clearer with conservation laws. Energy provides one example, but the same structure appears with momentum, electric charge, and rotation. These quantities move between objects, change form, or spread out, yet the total remains fixed. Nothing in the system tries to keep the total unchanged. The conservation appears only after everything settles. If an experiment ends with extra energy appearing from nowhere, the response is not excitement. The response is error, because the law does not bend. This shows another important feature. A law does not care about size. The same relationships apply to falling stones, moving planets, vibrating atoms, and distant galaxies. The numbers change, the units change, the surroundings change, the relationship stays. That wide reach is not assumed. It is earned through testing in many different situations. This is another place where expectations fail. People often expect rules to come from purpose or design. Physical laws come from neither. They are noticed because even disorder respects them. Chaotic systems obey laws just as strictly as neat ones. Wild air motion follows the same equations as smooth flow. A crashing wave respects conservation just as much as a clockwork machine. The law does not disappear when behavior looks messy. It remains in place because it never depended on tidy outcomes. This leads to an important clarification. A law does not guarantee prediction. It guarantees constraint. You may fail to predict what happens next, while still knowing certain outcomes will never appear. That certainty is where physics draws its strength, and this is where the word law earns its weight. A physical law is the strongest claim science makes, stronger than a model, stronger than a story, stronger than an explanation. It says, across all tested cases, under all accessible conditions, this relationship holds without exception. That does not make laws untouchable. New discoveries can refine them or reveal deeper structures beneath them. Even then, the older law survives inside its tested range. Newton's laws still guide bridges and baseballs. Ohm's law still guides circuits. Thermodynamic laws still govern engines and cells. The law remains because it was never about perfection. It was about consistency. At the deepest level, a law in physics is a statement about what stays fixed while everything else rearranges. It is the frame holding change together. And that brings back the question quietly waiting underneath all of this. If laws describe consistency rather than control, why does the universe show consistency at all? That question stays because laws do more than describe stability. They shape how reasoning itself works in physics. When a physicist faces a new situation, the first step is rarely prediction. The first step is elimination. A law immediately rules things out. You may not know what will happen when systems interact, but a law tells you what outcomes cannot appear under any arrangement. That power comes from the fact that laws apply before details are filled in. They operate at the level of structure, not outcome. This is how laws actually get used. Suppose two objects collide. You may not know their final speeds. You may not know the direction they move afterward. But conservation laws already fix the range of possibilities. Energy and momentum place boundaries around every allowed result. Any answer outside those boundaries is dismissed instantly, no matter how clever the explanation sounds. The law does not predict a single future. It restricts the space of futures. This is why laws remain useful, even when prediction fails. Weather cannot be forecast perfectly. Turbulence resists exact calculation. Human motion is wildly complex. Yet every one of these systems still obeys the same laws. Even when outcomes vary, relationships stay intact. This leads to a surprising result. Uncertainty in outcomes does not weaken laws. It highlights their role. A law remains exact, even when predictions are rough. That feels backward at first. People often expect exact laws to produce exact answers. Physics shows the opposite. Laws define constraints so strong that even randomness cannot escape them. This is easiest to see in statistics. Take a gas. Individual molecules move unpredictably. Collisions vary. Paths twist endlessly. Yet pressure, temperature, and volume stay linked by precise relationships. The law does not follow single particles. It governs the collective behavior without tracking details. Nothing in the gas coordinates. Nothing averages on purpose. The law emerges because every motion still respects the same restrictions. Here, a law does not describe what each piece does. It describes what the whole cannot avoid doing. This is one of the most counterintuitive features of physical laws. They grow stronger as systems grow more complex. That strength leads to consequences that often surprise people. One of them is this: multiple laws apply at the same time. No system ever follows just one law. A falling object respects gravity, energy conservation, momentum conservation, and constraints imposed by material strength all at once. These laws do not compete, they intersect. Each one trims the list of possible behaviors further. The final outcome sits at the intersection of all constraints. This is how physics stays coherent. You do not choose which law applies. All relevant ones apply together, automatically. The result is not negotiated. It is determined by compatibility. This explains why adding information does not remove laws. It narrows possibilities. Another surprising result follows from this. A law can remain correct even when the explanation behind it changes. This happens repeatedly in physics. Newton's laws described motion accurately long before deeper theories existed. Later work revealed broader frameworks that changed how motion was explained, yet Newton's laws stayed valid within their tested range. They never stopped working. They simply stopped being the deepest description available. That tells us something important about what laws are. They are not guesses about hidden causes. They are records of consistency. That is why laws age well. Now consider a paradox people often stumble into. If laws are descriptions written by humans, why do they feel so absolute? The answer lies in their origin. A law is not declared after a few successful tests. It survives relentless attempts to dismantle it. Physicists try extreme conditions, unusual materials, edge cases, and clever tricks. The law earns its status by refusing to fail. This gives laws a special role. They are not opinions strengthened by agreement. They are conclusions strengthened by resistance. That resistance shapes meaning. A law tells you something about the universe that remains true regardless of preference, perspective, or scale. It tells you reality has structure that does not bend to narrative. That realization carries weight beyond equations. It tells you the universe is not arbitrary. Events may appear chaotic, unpredictable, or complex, yet they unfold inside boundaries that never move. That makes explanation possible at all. Without laws, there could still be events. There could still be motion. There could still be change. But there could be no science. No comparison would hold. No experiment would repeat. No lesson would carry forward. A law gives memory to the universe. It allows the present to resemble the past in specific ways. And now the meaning comes into view. A physical law says that beneath all variation, something stays fixed. It says that while appearances change, relationships endure. It says that the universe does not reinvent itself moment to moment. That does not remove mystery, it sharpens it. Because laws answer how behavior stays linked while leaving the deeper question open, why this structure exists at all. Physics does not claim to answer that fully. It claims something narrower and more solid. It claims that whatever the universe is doing, it does so within limits that never waver. Those limits are what we call laws. They are not the actors in the story. They are the grammar. Without grammar, sounds still exist. With grammar, meaning appears. In the same way, events still happen without explanation. With laws, those events become intelligible. And that is why laws sit at the center of physics, not as commands, not as causes, not as decorations, as the unchanging framework that allows change to make sense at all. That realization tends to pull people forward because it suggests that learning physics is not about collecting facts. It is about learning the boundaries within which every fact must live. And those boundaries remain even as knowledge grows, even as explanations deepen, even as the universe continues doing what it has always done, behaving consistently without asking permission. At this point, the role of a law in physics comes into view without decoration. A law is not a belief about how the universe should behave. It is a record of how the universe has behaved every time we have been able to test it across places, scales, and conditions. It is a statement of consistency that reality keeps confirming. That consistency is what allows physics to function at all. After a law is established, it turns into a tool. It allows reasoning without seeing the outcome first. It allows confidence that certain results will never appear, even when the exact result remains unknown. That is the practical strength of a law. It does not describe the future in detail. It limits the future to a narrow range of allowed outcomes. This explains why very different systems can be discussed using the same laws. A swinging pendulum, a satellite orbit, and an electron bound in an atom behave differently, yet they remain tied to the same constraints. Surface details vary, the relationships remain. This also explains why laws survive progress. When physics advances, earlier laws are not discarded the way mistaken ideas are. They remain valid within the range where they were tested, even as broader descriptions add more structure underneath. Bridges still stand because Newton's laws hold. Circuits still function because electrical laws hold. Engines still run because thermodynamic laws hold. That persistence tells us something important about what is solid knowledge. Certain relationships hold without exception in every experiment performed so far. Energy does not appear from nothing. Momentum balances during interaction. Electric charge remains conserved. These statements are not guesses. They are the strongest claims science makes. At the same time, there are limits to what is known. Physics does not explain why the universe has laws rather than complete disorder. It does not explain why these particular relationships exist instead of others. It does not explain why consistency exists at all. Those questions remain open. That boundary between what is established and what remains unanswered is part of the structure, not a weakness. Laws tell us how far reasoning can go without speculation. They mark the edge where description ends and deeper explanation has not yet arrived. Taken together, this forms a clear world view. The universe is not free of constraint, and it is not fixed down to every detail. It operates within strict limits while allowing variation inside those limits. Events can surprise, yet they never violate the relationships holding everything together. That balance explains why prediction can be difficult while reliability remains absolute. It also explains why progress in science comes from tightening constraints rather than adding stories. Each new law or deeper version of an existing one removes possibilities rather than increasing them. That narrowing is progress. The takeaway is simple and strong. A physical law is the strongest form of knowledge available about the world. It does not tell us everything. It tells us what reality never does. That is enough. Because knowing what cannot happen allows technology to function, explanations to hold, and learning to continue without collapse. The universe may remain incomplete to us, but it is consistent. It behaves in ways that can be relied on, and every time a law holds, it confirms the same fact. The world is structured in a way that allows it to be studied, shared, and explained, again and again, without exception.
You've got a piece of glass, just regular glass like a window, and you shine light at it, what happens? Well, most of the light goes through, obviously, but some of it bounces back, reflects, about 4% actually. 4 out of every 100 photons hit that glass and decide to turn around. How does a photon decide? You've got 100 photons, all identical, all hitting the same piece of glass at the same angle. 96 go through, 4 bounce back. Why those 4? What makes them special? And if you think, well, maybe there are little imperfections in the glass, little spots that reflect and little holes that let light through. That's a reasonable guess, but it's wrong. You can polish glass until it's absolutely perfect at the atomic level, and you still get exactly 4% reflection. The photons aren't bouncing off imperfections, so maybe the photons themselves are different somehow, like they have little internal clocks or wheels that determine whether they'll reflect or pass through. That sounds crazy, but it's not a terrible idea. Except there's an experiment that completely destroys it. Take a very thin layer of glass, a film, 2 surfaces now instead of 1, a front surface and a back surface. If each surface reflects 4% independently, you'd expect to get about 8% total reflection, right? 4 from the front, roughly 4 from the back. Simple addition. But that's not what happens. Not even close. Depending on exactly how thick that glass layer is, you can get anywhere from 0% reflection to 16% reflection. 0, 16. The same glass, the same light, just different thicknesses, and the reflection swings wildly between nothing and quadruple what you'd expect. How is that possible? How can adding a second surface sometimes cancel out the reflection from the first surface? It's as if the back of the glass is somehow reaching forward in time and telling the front surface not to reflect. If you keep making the glass thicker, the pattern repeats over and over again, perfectly regular. With really precise equipment, you can see this pattern continue for millions of cycles. Millions. This isn't some small effect. It's absolutely fundamental to how light behaves. So what's actually going on? Well, here's where it gets genuinely strange. The explanation that works, the only explanation that matches all the experiments, is that light doesn't pick one path. It doesn't decide to reflect or not reflect. Instead, and I know this sounds completely insane, light takes every possible path simultaneously. When a photon hits that glass, it doesn't choose. It explores all options at once. It reflects from the front surface and passes through, and reflects from the back surface and passes through both, all at the same time. All of these possibilities happen together. Now wait, if everything happens, how come we see definite results? How come the detector either clicks or doesn't click? Here's the key. Each possible path carries what we call a probability amplitude. Think of it as a little arrow. And these arrows can point in different directions. When you add them together, arrows pointing the same way make the result bigger. Arrows pointing opposite ways cancel each other out. So when light goes through thin glass, the arrow from reflecting off the front surface and the arrow from reflecting off the back surface, they might point in the same direction. Add them up, you get a big arrow, and that means high probability of reflection, 16% instead of 8. But if the glass is a slightly different thickness, those arrows might point in opposite directions. They cancel perfectly, 0 reflection. The light from the front and the light from the back interfere destructively. They literally eliminate each other. And this isn't just glass, this is everything. Mirrors, lenses, rainbows, the color of the sky, why metals are shiny, why water is transparent, all of it comes down to these little arrows adding up or canceling out. All of it requires that light explores every possible path simultaneously. The theory that describes this, it's the most precise theory in all of science. It makes predictions accurate to 12 decimal places. If you measured the distance from Los Angeles to New York, this theory could tell you the answer to within the thickness of a human hair. That's how good it is. But ask any physicist to explain why light behaves this way, why it explores all paths, why probability works through these little arrows. They can't tell you. Not because they haven't thought about it. They have. Generations of brilliant people have tried. The answer is, we don't know. Nature just works this way. Think about a regular mirror. You probably learned that light bounces off a mirror according to a simple rule. Angle in equals angle out. That's true. But why? The explanation you probably heard is that light travels in straight lines and bounces like a ball. Light actually bounces off every part of the mirror, not just the middle part where the angles match. Every single part, even the edges, even the corners. The light bouncing off the far left edge of your mirror is absolutely real. It exists. It's happening. So why do we only see the reflection from the middle, where the angles match? Because of those arrows again. The paths from the middle of the mirror all take roughly the same amount of time to get from the source to your eye. Their arrows point in similar directions. They add up. They reinforce each other. But the paths from the edges, they take different amounts of time. Very different. So their arrows spin around and point every which way. One edge contributes an arrow pointing up. The next spot contributes one pointing down. They cancel. The contribution from the edges just disappears. You can actually prove that light bounces off the edges of a mirror. If you take that mirror and very carefully scratch away parts of it, not randomly, but in a precise pattern, removing the parts that would contribute arrows pointing in the wrong directions, suddenly the edge of the mirror starts reflecting like crazy, at angles that should be impossible. This is how a diffraction grating works. It's literally just a mirror with most of it blocked off in a clever way, so the cancellation doesn't happen anymore. So light doesn't know the law of reflection. It doesn't know that angle in should equal angle out. It just goes everywhere, and the mathematics of those arrows adding up makes it look like there's a simple rule. The same thing explains why light bends when it enters water. It's not because light knows to slow down and change direction. Light takes all paths through the water simultaneously. The paths where it would bend the wrong amount cancel out. Only the paths where it bends just right, following what we call the law of refraction, those are the ones where the arrows line up. Think about that. Every simple rule you learned about light in school is actually a consequence of something much deeper and much stranger. Light explores every possibility, and the rules emerge from interference between all those possibilities. This is what physics discovered in the 20th century, and honestly, it's never made complete sense to anyone, not intuitively. You can calculate with it perfectly. You can build lasers and fiber optics and all sorts of technology based on it. But understanding it, feeling like you really get why nature works this way? All right, so now we need to go deeper. Because what I've told you so far is just about light bouncing around. But light does more than bounce. It interacts with matter, with electrons. And this is where things get, well, even more absurd. Here's what we know for certain. In the entire universe, when it comes to light and matter, there are only two kinds of particles that matter. Just two. Photons, which are particles of light, and electrons, which are particles of, well, stuff, matter, the things that make atoms work. That's it, two players. And everything you see around you, every color, every reflection, every shadow, the fact that you can see it all, comes from these two particles doing a very simple dance. There are only three things that can happen. Three basic actions, that's all. First, a photon can travel from one place to another. It just moves through space and time. Second, an electron can travel from one place to another. Same idea. And third, and this is the important one, an electron can absorb or emit a photon. Three actions. That's the complete list. Everything else, everything, is just combinations of these three things happening over and over again in different arrangements. Think about what that means. When you see a red apple, what's happening? Photons from the sun hit electrons in the apple's surface. Those electrons absorb the photons, jiggle around, and emit new photons. The red photons happen to be emitted more than blue ones because of how the electrons in that particular molecule are arranged. Those red photons travel to your eye, hit electrons in your retina, get absorbed, and trigger a chain of events that eventually becomes the experience of seeing red. All of it. Every step is just those three actions. Photon moves, electron interacts with photon. Over and over and over. Now here's where it gets mathematical. Not in a complicated way, but in a surprising way. Each of those three actions has a number associated with it. A probability amplitude, one of those little arrows we talked about. For a photon traveling from point A to point B, there's an arrow. For an electron traveling from A to B, there's an arrow. And for the interaction, when an electron emits or absorbs a photon, there's an arrow too. The arrow for the interaction is always the same size. Always, no matter what. It's a single number, roughly 0.1. Or if you want to think about probability, you square it and get about 1%. 1 in 100. This number is, it's one of the most mysterious things in all of physics. It shows up everywhere. It determines how strong the electromagnetic force is. It controls how atoms hold together. It sets the scale for all of chemistry. And nobody, absolutely nobody, knows where it comes from. You can measure it incredibly precisely. It's approximately 1 divided by 137, or about 0.0073. Physicists call it the fine structure constant. And if you ask why it has that value instead of some other value, you get silence, confused looks, maybe some speculation, but no answer. It's like asking why the speed of light is what it is, or why the electron has the mass it has. These are numbers we can measure, but cannot explain. They're just facts about the universe, brute facts, with no deeper reason that anyone has found. So we've got these 3 actions and their arrows. Now, to figure out what actually happens in any situation involving light and matter, you do something remarkable. You draw pictures. Not just any pictures, very specific diagrams. You draw all the possible ways something could happen using just those 3 basic actions. A photon goes here, hits an electron. The electron moves, emits a photon. That photon goes somewhere else. Every possible sequence. And then you calculate the arrow for each diagram by multiplying together all the individual arrows for each action in that diagram. Photon travels, multiply by its arrow. Electron travels, multiply by its arrow. Interaction happens, multiply by 0.1. After you've got all the diagrams and all their arrows, you add them up. Just like before with the mirror. Some arrows reinforce, some cancel. The final arrow you get, you square it, and that's your probability. Every time you have an interaction, an electron emitting or absorbing a photon, you multiply by that small number, roughly 0.1. So a diagram with 1 interaction has a factor of 0.1. A diagram with 2 interactions has 0.1 times 0.1, which is 0.01. 3 interactions gives you 0.001. The more complicated the diagram, the smaller its contribution. This is why physics can make predictions at all. The simplest diagrams matter most. The complicated ones contribute less and less. You can ignore most of the infinite possibilities because their arrows are too tiny to matter. But you can't ignore all of them. And this is where the precision comes from. If you want really accurate predictions, you have to include more and more complicated diagrams. Each one adds a tiny correction. And when you add up thousands of these corrections, the predictions match experiments to 12 decimal places. 12. That's like measuring the distance across a country and getting it right to within a hair's width. No other theory in all of science comes close to this level of accuracy. Now here's something that seems like it shouldn't work, but does. In these diagrams, photons can do things that seem impossible. They can travel backwards in time. They can go faster than light. They can have negative energy. Wait, what? How can that be allowed? The key is that these weird photons never get observed directly. They're called virtual photons. They exist only as intermediate steps in a calculation. A real electron over here emits a virtual photon. That virtual photon does something impossible, like traveling backwards in time, and then another electron absorbs it. The end result is just 2 electrons pushing each other apart. You never see the virtual photon. You can't catch it with a detector. It only exists as a way of describing the interaction mathematically. And here's what's wild. You have to include these impossible paths. If you only counted the sensible-looking diagrams, you'd get wrong answers. The theory only works when you let photons do crazy things in the middle of the calculation, even though the final answer always describes something perfectly reasonable. This is what physicists mean when they say nature is absurd. Not absurd in a random way, absurd in a very precise, very specific way that gives exactly correct predictions. The rules seem crazy, but they work. Here's the question that haunts everything. Why these rules? Why does the interaction strength have that particular value? Why do the arrows add the way they do? Why does probability come from squaring the arrow instead of cubing it or taking the absolute value or something else? Nobody knows. These questions have been asked for almost a century now. The best minds in physics have wrestled with them, and we're no closer to answers than we were in the beginning. The theory works. It's the most successful theory humans have ever created. But understanding why it works, that's still out of reach. And there's a certain kind of honesty in admitting that. Science isn't about pretending to know everything. It's about being precise about what we do know and clear about what we don't. We know how light behaves. We can calculate it with extraordinary precision. Why it behaves that way? That's still a mystery. Maybe someday someone will figure it out. Maybe the answer is waiting in some equation nobody has written yet. Or maybe some things just are the way they are. And asking why is like asking why the number 3 is odd. It just is. But until we know for sure, we keep calculating, we keep testing, we keep pushing the precision higher and higher, looking for any crack in the theory that might give us a hint about what's underneath. So far, no cracks. Just this strange, beautiful, completely absurd picture of light, exploring every path at once, and the mathematics somehow always getting the right answer. So let's bring this all together, because there's something deeply unsettling about what we've discovered, and I think it's worth sitting with that discomfort for a moment. We started with a simple question: how does light work? And the answer turned out to be, light explores every possible path simultaneously. It doesn't choose. It doesn't decide. It just does everything at once, and the mathematics of interference picks out what we actually observe.
That's weird enough. But then we went deeper. We found that all interactions between light and matter come down to just 3 basic actions. Photon moves, electron exchanges photon. That's the whole story. And these actions combine according to rules involving little arrows, probability amplitudes, that add up and cancel in ways that perfectly predict what happens. When you really understand this picture, you realize something troubling. The world we see, the world of solid objects and definite events and light traveling in straight lines, that world is a kind of illusion. Not an illusion in the sense that it's fake, it's real, but it emerges from something much stranger underneath. Underneath, there are no straight lines. There are all lines, every possible path happening together. Underneath, there are no definite outcomes until something is measured. Just amplitudes, just possibilities, all superimposed. The classical world we experience is what you get when trillions of these quantum events average out. The arrows that point at every which way mostly cancel. What survives is the sensible-looking stuff, the stuff that matches our intuition. But that intuition is just a consequence of scale. At our size, the weirdness hides. This isn't a limitation of our knowledge. It's not that we haven't figured out the deeper mechanism yet. As far as anyone can tell, there is no deeper mechanism. The quantum level is the bottom. The arrows and the interference and the probability, that's what reality actually is. You might think, okay, but surely there's some hidden variable we haven't found, some underlying clockwork that determines which photon reflects and which one passes through. Some explanation that would make everything deterministic again, like classical physics was. People have looked. For almost 100 years, people have looked. They've done incredibly clever experiments designed to catch nature hiding information from us. And every single time, nature isn't hiding anything. The randomness is real. The probability is fundamental. There's no secret script determining outcomes in advance. This was hard for a lot of physicists to accept. Some of the greatest minds of the 20th century spent decades trying to find a way around it. They couldn't. Not because they weren't smart enough, but because there doesn't seem to be a way around it. This is just how reality works. Physics gave up on something. It gave up on the idea that we can, even in principle, predict exactly what will happen. The best we can do, the absolute best, with perfect knowledge of everything, is calculate probabilities. That's it. That's the ceiling. And you know what? The theory that accepts this limitation is the most accurate theory humans have ever produced. By a huge margin. It's not even close. So whatever discomfort we feel about probability being fundamental, nature doesn't seem to share that discomfort. There's a tendency to believe that science explains things, that when you really understand something, you can say why it happens. But that's not quite right. Science describes things. It tells you how things behave
with incredible precision. But the why questions, they often don't have answers. Why does the interaction between light and matter have strength 1 over 137? Nobody knows. Why does probability come from squaring the amplitude? Nobody knows. Why do the rules of quantum mechanics look the way they do instead of some other way? Nobody knows. These aren't questions that science has failed to answer. They're questions that might not have answers at all. Or if they do have answers, those answers might just push the mystery back one level. You explain this in terms of that, and then you have to explain that in terms of something else. And eventually you hit bottom. You reach the place where the only honest thing to say is, this is just how it is. You have to be comfortable with that. You have to be okay with not knowing. Not fake okay, where you pretend the question doesn't bother you. Actually okay. Because the universe doesn't owe us explanations that fit our intuitions. It doesn't owe us answers that feel satisfying. It just does what it does. And our job is to describe that as accurately as possible. The strange thing is, once you accept this, the weirdness becomes kind of beautiful. Light exploring all paths at once isn't just bizarre, it's elegant. All of chemistry and biology and material science emerging from 3 simple actions isn't just surprising, it's profound. The fact that we can predict anything at all in a universe this strange is remarkable. This picture of reality, with its probability amplitudes and interference and particles doing impossible things when nobody's looking, it didn't come from philosophy. It didn't come from pure thought. It came from experiments. People measured things, found results that didn't make sense, and were forced to invent new concepts to describe what they saw. Nature dragged us, kicking and screaming, to this understanding. We didn't want quantum mechanics. We didn't ask for probability to be fundamental, but the experiments left no choice. And that's how science works. You don't get to pick what's true. You follow the evidence wherever it leads, even if it leads somewhere uncomfortable. We have a theory that works spectacularly well. A theory that says light is both simpler and stranger than anyone imagined. 3 actions, little arrows, interference. That's enough to explain every optical phenomenon ever observed. Every color, every reflection, every rainbow, every laser. But we don't understand why this theory is true. We don't know where the rules come from. We don't know if they could have been different, or if there's some deeper principle that makes them inevitable. And maybe that's okay. Maybe the honest answer is, we're still figuring it out. Science isn't finished. It might never be finished. There might always be another layer, another mystery, another question that we can't quite answer yet. But look how far we've come. 100 years ago, we didn't even know light came in particles. Now we can predict its behavior to 12 decimal places. We can build lasers and fiber optics and technologies that would have seemed like pure magic to earlier generations. The universe is stranger than we ever imagined. And somehow, against all odds, we're starting to figure it out.
Time doesn't exist, at least not the way you think it does. Not as this universal clock ticking the same for everyone. That's an illusion. And once you understand why, you'll never look at your watch the same way again. Every clock on Earth is lying to you. The one on your wall, the one on your wrist. And I don't mean they're broken or poorly calibrated. I mean something much more disturbing. There is no such thing as the correct time. Now you might be thinking, wait a minute, that's ridiculous. We all agree what time it is. Noon is noon. Midnight is midnight. We synchronize our clocks and they all say the same thing. And yeah, sure, for everyday life, that works well enough. But here's the thing. It only works because we're all moving slowly. Very, very slowly compared to light. And we're all sitting in roughly the same gravitational field. The moment you change either of those conditions, your clock starts lying to you. Or more accurately, you realize it was never telling you the time. It was only telling you its time. Here's the secret. Time is personal. Time is local. Your clock measures your time. My clock measures my time. And these 2 times are not necessarily the same. So, let me explain what I mean by that. Because this isn't philosophy. This isn't some abstract idea you can argue about. This is measured. This is tested. This is real. Imagine you have 2 identical clocks. Perfect clocks. The best clocks anyone could ever build. You synchronize them perfectly. They tick together. They agree completely. Now you take one of those clocks and you put it on an airplane. You fly it around the world. And then you bring it back and compare it to the clock that stayed on the ground.
They don't agree anymore. The clock that flew is behind. It's ticked fewer times. It's measured less time. And this isn't because the airplane vibrations messed it up, or because the pressure was different, or any mechanical explanation like that. No. Time itself passed more slowly for the moving clock. Now watch. This was actually done. In 1971, scientists put atomic clocks on airplanes, flew them around the world in both directions, and compared them to clocks on the ground. The results matched the predictions exactly. Time runs differently depending on how you're moving. But wait, there's more. It's not just motion that affects time, gravity does too. A clock at the top of a tall building runs faster than a clock at the bottom. Not by much, we're talking billionths of a second. But it's real, it's measurable. The clock closer to the Earth, deeper in the gravitational field, ticks slower. So what does this mean? It means time isn't this universal thing flowing at the same rate everywhere. Time is flexible. Time is stretchable. Time is, well, personal. And this leads to something even stranger. The concept of now itself becomes meaningless. The twist, think about it. When you say right now, you're assuming there's some universal moment that applies everywhere. That right now, as you're listening to this, there's also a right now on Mars, a right now in the Andromeda Galaxy, a simultaneous moment across the entire universe. If you're standing still on Earth, you have one definition of now. If you're flying past Earth at high speed, you have a different definition. Events that are simultaneous for you are not simultaneous for the moving person, and neither of you is more right than the other. This is hard to accept, I know. We grew up thinking of time as this absolute thing, this river flowing at the same rate everywhere, this background against which events happen. But nature doesn't care about what we grew up thinking. Nature does what nature does. And what nature does is far stranger than our intuitions. Here's why this matters. For most of human history, we thought space and time were completely separate things. Space was the stage. Time was the clock on the wall. They had nothing to do with each other. Then along came relativity and showed us that's completely wrong. Space and time are not separate. They're woven together into a single fabric. We call it space-time. And everything that happens in the universe happens in space-time. You cannot talk about where something is without also talking about when it is. They're part of the same measurement, part of the same reality. So let me give you an analogy. Imagine you're looking at a map. On this map, there's north-south and there's east-west, two different directions, perpendicular to each other. Now imagine two people standing in the same spot, but facing different directions. One person faces exactly north. For him, north and east are clearly different directions, no confusion. But then the other person faces northeast. For him, what he calls forward is partly north and partly east. His forward is a mixture of the first person's north and east. Neither person is wrong, they're just using different reference frames. What's purely north to one person is partly forward and partly sideways to another. Space and time work the same way. What looks like pure time to someone standing still looks like a mixture of time and space to someone moving. They're not separate things. They're different directions in space-time. And how you divide them up depends on your motion. That's the key. When you move through space, you're also affecting how you move through time. There's a trade-off. The faster you move through space, the slower you move through time. And this isn't a metaphor. This is literally what happens. Everything moves through space-time at the same total speed. Always. You can't avoid it. When you're sitting still, not moving through space at all of your motion through space-time is directed through time. Time flows at its maximum rate for you. But when you start moving through space, some of your space-time motion gets redirected. Less of it goes through time. So time slows down for you compared to someone who's standing still. Now you might ask, okay, but if time slows down when I move, why don't I notice it? And that's a great question. The answer is because everything slows down together. Your clock slows down. Your heartbeat slows down. Your thoughts slow down. Every process that could possibly measure time slows down by exactly the same amount. So from your perspective, everything feels normal. It's only when you compare your experience to someone else's, someone who is moving differently, that the difference shows up. Your clock and their clock no longer agree. Your time and their time have diverged. And here's the shock. This isn't a small effect at high speeds. If you could travel at 99% the speed of light, time would slow down by a factor of about 7. 1 year for you would be 7 years for people back on Earth. Get even closer to light speed, 99.9%, and the factor becomes about 22. You could take a trip for a few years, come back, and centuries could have passed on Earth. You could outlive everyone you know. You could see the far future, not by living longer, but by having time pass more slowly for you while the rest of the universe ages. This is real. This is how the universe works. Time is not what you thought it was. Well, nature doesn't think in terms of space and time separately. Nature thinks in terms of space-time. And once you start thinking that way too, everything starts to make sense. Imagine you're driving your car on a road. The road goes north. You can measure how far north you've gone. Simple enough. But now the road curves. It starts going a little bit east as well as north. Now, for every mile you drive, you're not going a full mile north anymore. Some of your motion is being spent going east. The total distance you travel along the road stays the same. But how that distance gets divided between north and east, that changes depending on the direction of the road. Here's the truth. Space-time works exactly like this. There's a kind of distance in space-time, and everything travels through space-time. But how that travel gets divided between space and time depends on your motion. When you sit still, all your travel through space-time goes through time. You're not moving through space, so you move through time at the maximum rate. When you start moving through space, some of your space-time travel gets redirected into space. Less of it goes through time, so you age slower. Your clocks tick slower. Time dilates. It's not magic, it's geometry. It's the geometry of space-time. Now, this might sound abstract, so let me make it more concrete. There's a quantity in space-time that everyone agrees on. No matter how fast you're moving, no matter where you are, this quantity is the same. We call it the space-time interval. Think of it this way. In regular space, if I measure the distance between 2 points, I might get a different answer than you if we're using different coordinate systems. Maybe I'm measuring in one direction and you're measuring in another. We disagree about how far east something is or how far north. But the actual distance between the points, the straight line distance, that's the same for everyone. It doesn't matter how you orient your rulers. The distance is the distance. The key insight, space-time has something similar. There's an interval between two events, not just 2 points in space, but 2 events in space-time, meaning 2 locations that also have times attached to them. This interval combines both the spatial separation and the time separation. And just like the distance in regular space, this interval is the same for everyone. You might disagree about how much of it is space and how much is time, but the total interval, that's invariant. That's a fact of nature that doesn't change based on your perspective. So, when we say space and time are the same thing, we don't mean they're identical. Obviously, time feels different from space. You can walk backwards in space, but you can't walk backwards in time. There are differences. What we mean is that they're connected. They're part of the same geometric structure. You can trade one for the other, depending on how you're moving. But the underlying structure, the space-time itself, that's absolute. That's real. That's what nature actually cares about. But wait, we've been talking about motion. But what about gravity? How does gravity fit into all this? And this is where things get really interesting. See, for a long time, people thought of gravity as a force. You know, the earth pulls on you, you pull on the earth, there's this invisible rope connecting everything with mass. And for most purposes, that works fine. You can calculate orbits, predict falling objects, send rockets to the moon. But that picture is incomplete. It doesn't explain why gravity affects time. It doesn't explain why clocks at different heights run at different rates. Something deeper is going on. Here's what's really happening. Mass curves space-time. The Earth doesn't reach out and grab you with some invisible force. Instead, the Earth bends the space-time around it, and you, moving through that curved space-time, follow the natural path, which happens to curve toward the Earth. You feel this as falling, but really you're just moving in a straight line through curved space-time. It's the space-time itself that's bent. And here's the beautiful part. Because space-time includes time, when space-time is curved, time is curved too. Near a massive object where space-time is more curved, time runs slower. Not because some force is acting on your clocks, but because the very fabric of time is stretched. Really think about that for a moment. Time isn't just affected by gravity. Time is part of what gravity bends. You know, people often think of curved space and have trouble visualizing it. What does it mean for space to be curved? Curved into what? But actually, that's the wrong question. Space doesn't have to be curved into anything. The curvature is intrinsic. It's a property of the space itself. Let me give you an example. Imagine you're an ant living on the surface of a balloon. You can only move on the surface. You can't go up or down. You can only crawl along the balloon's skin. For you, the balloon's surface is the entire universe. It's two-dimensional, but it's curved. If you walk in what feels like a straight line, you'll eventually come back to where you started. The surface wraps around. Now, we standing outside can see that the balloon is curved in three-dimensional space, but you, the ant, can figure out the surface is curved without ever leaving it. You can do experiments. You can measure angles of triangles. You can notice that the rules of flat geometry don't quite work. The surface itself has curvature, and you can detect it from the inside. Now watch this. Our space-time is the same way. It's curved. We don't need to ask, curved into what? Because the curvature is detectable from within space-time itself. We measure it by watching how clocks run at different rates, how light bends near massive objects, how objects accelerate toward each other without any force pushing them. This isn't philosophy. This is physics. This is measurable. And here's where time comes back in. The curvature of space-time near Earth is mostly curvature of time, not space. Space itself is barely curved at all near Earth. But time is significantly curved. That's why clocks at different heights tick at different rates. That's why falling objects accelerate. The time curvature is the dominant effect. So, when you drop a ball and watch it fall, what's really happening? The ball is moving through curved space-time. It's following the straightest possible path, what we call a geodesic, through that curved geometry. And because time runs slower closer to the Earth, that path curves downward. You think gravity is pulling the ball, but actually, the ball is just moving naturally through curved space-time. There's no force, just geometry. The twist here, this explains something that puzzled physicists for centuries. Why does gravity affect all objects the same way? A feather and a hammer in a vacuum fall at exactly the same rate. Why? If gravity were a force, you'd expect heavier things to feel a stronger pull. But they also have more inertia, more resistance to acceleration. These two effects exactly cancel. It seems like a coincidence, a very precise, very suspicious coincidence. But in the space-time picture, it's not a coincidence at all. Objects aren't being pulled. They're just moving through curved space-time. And the path through curved space-time doesn't depend on what the object is made of or how heavy it is. The geometry is the geometry. Everything follows the same curves. This is profound. Gravity isn't a force. Gravity is the shape of space-time. And time is part of that shape. So when I say time doesn't exist, what I mean is that time as this separate, independent, universal thing doesn't exist. Time as a river flowing at the same rate everywhere doesn't exist. That's an illusion created by our slow speeds and weak gravitational fields. What exists is space-time, this unified four-dimensional fabric that can be curved, stretched, and warped by the presence of mass and energy. Time is woven into this fabric, inseparable from space, relative to motion, affected by gravity. Your clock doesn't measure the time. Your clock measures its own journey through space-time. Nothing more, nothing less. And that's the truth. But if time is so flexible, if it's different for different observers, what's actually real? Is anything real? Or is everything just perspective? And this is where it gets beautiful. Because yes, some things are real. Absolutely, unchangeably, observer independently real. They're just not what you expected. The space-time interval between two events, that's real. Everyone agrees on it. The laws of physics themselves, those are real. They work the same way for everyone, no matter how fast they're moving. The speed of light, that's real. It's the same in all directions, for all observers, always. Here's the secret. What's relative is how you slice up space-time into space and time. That's a choice. That depends on your motion. But the space-time itself, the underlying four-dimensional geometry, that's absolute. It's like, imagine a loaf of bread. You can slice it straight across, or you can slice it at an angle. Different slices, different shapes. But the loaf itself doesn't change. The bread is the bread. Space-time is the loaf. Your now, your simultaneous moment across the universe, that's just one slice. Someone moving differently makes a different slice. But the loaf itself, the totality of all events in space-time, that's the same for everyone. So reality exists. It's just more subtle than we thought, more geometric, more unified. And now comes the shock. This picture of space-time, this four-dimensional block of reality, it has a disturbing implication. If the past and future are just different regions of space-time, and space-time is real, then in some sense, the past and future are just as real as the present. Think about it. The year 1800 exists in space-time. So does the year 3000. They're not gone or not yet happened. They're just in different locations in the four-dimensional structure. Your experience of now, moving forward through time, that's something happening within space-time, not something happening to space-time. Physicists call this the block universe view. All of time exists simultaneously, laid out like a landscape. We experience moving through it, moment by moment, but the landscape itself just is. Now, I'm not saying this is definitely true. There are debates about this. Philosophers argue, physicists argue. It's not settled. But what is settled is that our naive view of time is wrong. The common sense idea that the present is special, that the past is gone, that the future doesn't exist yet, this view is incompatible with what we know about space-time. Something stranger is going on. We just don't fully understand what. But wait, there's more. Let's talk about something practical, something that shows this isn't just abstract philosophy. You've probably heard of those incredibly precise clocks, atomic clocks. They use the vibrations of atoms to keep time. They're so accurate that they would only lose or gain 1 second over millions of years. These clocks are sensitive enough to detect the time dilation from gravity, even just from being a few feet higher or lower. Scientists have measured this. A clock on a table runs at a slightly different rate than a clock on the floor. The difference is tiny, fractions of a billionth of a second, but it's there. So, what does this mean for your life? Well, technically, your head is aging faster than your feet, because your head is farther from the center of the Earth in a slightly weaker gravitational field. Time runs slightly faster there. Don't worry, the difference over an entire lifetime is about a billionth of a second. You won't notice, but it's real. Your head and your feet are in slightly different time zones. And it gets weirder. The atomic clocks used for navigation, these systems need to account for both effects. The clocks are moving fast, which slows time down, but they're also higher up, which speeds time up. The two effects work in opposite directions, and the engineers had to calculate both precisely to make the system work. If they ignored relativity, if they assumed time was absolute and universal, the system would fail within hours. Errors would accumulate. The whole thing would be useless. So this isn't abstract. This is engineering. This is practical. Relativity isn't just a theory. It's a fact that we rely on every day.
The truth is, we live in a relativistic universe. We always have. We just never noticed because we move slowly and live in weak gravity. Our intuitions evolved for the African savanna, not for high-speed travel or black holes. But now we know better. We've done the experiments, we've made the measurements, and the universe has told us in no uncertain terms that time is not what we thought.
Now let me leave you with something to think about. We started by saying your clock is lying to you. And in a sense, that's true. Your clock tells you its own personal time, not some universal time. It measures its own journey through space-time. But in another sense, maybe your clock is the only one telling the truth. It's telling you your time, the time you experience, the time that matters to your life, your aging, your existence. There's no cosmic clock in the sky keeping the real time. There's no universal present moment spreading across the cosmos. There's just space-time, and each of us traces our own path through it. When you really think about this, it's humbling. We walk around thinking we understand reality. We think time flows like a river, and space sits there empty and passive. We think our experience is how things actually are. But nature doesn't care about our expectations. Nature is deeper than we imagined, more connected, more geometric, more strange. And the beautiful part? We figured this out. Humans, on this tiny planet, orbiting an ordinary star, in one galaxy among billions. We looked carefully at nature, did experiments, followed the logic, and discovered that space and time are woven together, that gravity bends space-time, that the universe is far more elegant and far weirder than anyone expected. That's the power of physics, not just collecting facts, but finding the hidden structure underneath, the simple principles that explain complicated phenomena, the deep truths that were always there, waiting to be discovered. Time doesn't exist the way you thought, but what does exist is more beautiful, more subtle, and more connected than anything we could have imagined. And we're still learning. We still don't have all the answers. Space-time near black holes, at the very beginning of the universe, at the smallest scales, there's still mystery there, still questions, still discoveries waiting to be made. That's what makes this exciting. That's what makes physics worth doing. We've learned so much, and there's still so much more to learn. So keep asking questions, keep being curious, keep looking at the world and wondering what's really going on. Because when you do that, when you refuse to accept easy answers and dig for the truth, you become part of this incredible tradition, this human tradition of figuring out the universe, piece by piece, experiment by experiment, insight by insight. And who knows, maybe the next breakthrough will come from someone just like you.